The PCM 7140 is a series of laser diode driver modules that provides from 0.1 to 200 amps of pulsed current at frequencies up to 100 kHz and compliance voltages up to 60 volts. With three configurations covering a wide range of operating conditions, this versatile module is ideal for a wide variety of high-power pulsed laser applications, including OEM as well as research and development, diode characterization, burn-in, and life testing.
Hello, my name is James Budai. I'm the design engineer for the PCM 7140, and I'm here to introduce it to you today. What's in the box when you order the PCM 7140? You receive the module itself, shown in the upper right-hand corner. You receive a control cable, a manual control board, which is in the lower left, and the cable to connect it to the module, input-output cable, and the output board and manual. Here you see the front and rear view of the module. On the left-hand side you see J1. That's where you put in the high voltage input and the DC output. And J3 is the control cable, and J2 is the monitor, the current monitor. And if you look to the right of the current monitor, we have a potentiometer that you can adjust the output current and a status LED. On the right hand side you can see the liquid connections. There are three models of the PCM 7140 available. There's a 200 amp, a 10 amp, and a 1 amp. The 200 amp has output currents from 5 amps to 200 amps and rise and fall times less than 20 microseconds. The 10 amp version has output currents from 1 amp to 10 amps and rise and fall times less than 12 microseconds. And the 1 amp version has output currents of 100 milliamps to 1 amp with rise and fall times of less than 5 microseconds. So all the modules have the following in common with one another. All of them have current monitors. All of them have an internal potentiometer and analog control of the output current. All of them have error detection. They can detect an open load or an over temperature fault. And all of them are liquid cooled, and they require a 1 liter to 6 liter a minute flow rate with an input temperature of 11 degrees to 22 degrees Celsius. And they all have copper hose connections that are 3/8 inch tubing. Here is the input control board. This is something we think that you would use when you bring it up on your bench the first time to see how it operates. It makes it easier to connect and for you to play around with it to see if it's something you want to include in your OEM project. The bottom shows a 12 volt input. Those are banana jacks, so you can use common banana jacks to give 12 volts to the system. On the right hand side we have two SMB connectors, one for the gate input and one for the current set point. The current set point is an analog voltage that you can put in to adjust the output current. On the top is S1. It's two dip switches that are used to control who is controlling the output current. You can use the internal pot, or you can use the pot on this board, R40, or you can use the analog signal on J11. Here's the output board. The output board will connect to the cable that we've shipped with it, but you can connect your load to it. So we have a C mount and an F mount laser, and you could use any through-hole laser using the upper right-hand pad that says plus. On the back side of the board is a negative terminal. On the top where it says optional connector, that's a DB37 pin connector that we use internally here to test with our high current, low inductive loads. And that's an option that if you have the load, you can put that connector or just don't load it. Here's a mechanical outline of the device. I've shown J1 and J3 connected to the device, so that's how far out the connectors go when you put the mating connector in. And so you could see that it's roughly 4.5 inches by 4.5 inches by about 4 inches tall. There are 3 mounting holes that use 632 screws no more than a 1/2 inch long to mount to your shelf or anything you want to mount to. Let's first cover the 200 amp unit. So we've optimized the rise and fall times for full scale current, about 50% maximum current to 100% maximum current of the unit. So you'll notice that we have faster rise times as we increase the current. So from 5 amps to 49 amps on this module, we have less than 20 microsecond rise and fall. At 50 amps to 99 amps, we have less than 16 microseconds and less than 10 microseconds if we're above 100 amps. If you look at the oscilloscope trace, you can see we're at full scale current, 200 amps, and we have less than 6.5 microsecond rise and fall. We're allowing loads from 0 to 55 volts on the output. This can operate from single shot to 5,500 hertz, and you can run at 100% duty cycle from 5 amps to 20 amps. This graph shows the maximum duty cycle versus output current. So we have output current on the x-axis and duty cycle on the y-axis. This is one of 2 graphs. I'm going to have, the next slide's going to be another graph that shows the safe operating area. So what it shows us is output current on the x-axis, frequency on the y-axis, and then we're plotting different pulse width outputs. So if, for example, we wanted to output 175 amps and we wanted a 300 microsecond pulse width, we can follow 175 amps up from the x-axis until we hit the green line, which is 300 microseconds. And then we follow that over to the y-axis and see that the maximum frequency you can operate there is 90 hertz. Likewise, this is giving us similar information. We have the current on the x-axis and pulse width on the y-axis, and we're plotting different frequencies. So if, for this example, if you wanted to output 100 amps and you wanted to run 50 hertz, which is the blue line, follow that over to the y-axis and you can see that your maximum pulse width would be 1100 microseconds. Moving on to the 10 amp unit. The rise and fall times are similar to the 200 amp unit. So from 1 amp to 3 amps, we are less than 12 microsecond rise and fall. From 3 amps to 5 amps, we're less than 3 microseconds rise and fall. And greater than 5 amps, we are less than 2 microseconds rise and fall. Looking at the oscilloscope shot at 10 amps, we are at 1.3 to 1.1 microseconds. The forward voltage on this unit is 0 to 65 volts. The frequency range is single shot to 120 kilohertz. And we can run 100% duty cycle throughout the entire current range of this module as long as the V input voltage is set properly. This is a safe operating area graph similar to what we saw on the 200 amp unit. I'm just not going to go through any examples on this. Here's the other one that plots pulse width. Moving on to the 1 amp unit, we have less than 5 microseconds from 100 milliamps to 499 milliamps, and less than 2 microsecond rise and fall for 500 milliamps to 1 amp. Forward voltage is once again 0 volts to 65 volts, and frequency range is single shot to 100 kilohertz, and we can run 100% duty cycle through the entire current range. Once again, we have the safe operating area graphs. Setting up the instrument. So we're going to go through setting up the instrument from the time you open the box till we get a functional output. So first open up the box, and inside you'll see another white box. Go ahead and open that box. Inside the top box you'll find the operating manual and the cables that were mentioned in the earlier slide and the two printed circuit boards. These parts that are shown, we're going to set them aside and not use them. So in the middle are 4 rubber feet that you could put on the instrument if you're not going to mount it to a box. It'll help it from sliding around on your workbench. And also the OEM cable. This cable could be used in your OEM application. We're not going to use it for this video. So setting up all the parts. So first we'll set the input-output cable, which is J1, and we'll set up the control cable, which is J3 on the module, going to our manual control board. Next we'll connect our load. We'll connect the input-output cable to our load board. And if you notice, the optional DB37 pin connector is installed on the load board here. And this is our internal test load. It happens to be 0.1964 ohm, and that's what we're going to use to test this module. Next, we'll connect the input-output cable to a DC power source. This would be our V input. So we want to install an SMB to BNC cable to the function generator and place it on the gate input J12 on our manual control board. Next, we'll connect the liquid hoses, the water hoses in this case, to the copper pipes and enable and turn on our chiller or house water in this case and make sure there were no leaks. And we're going to leave the water on for the rest of this video. Next, we'll install the SMB to BNC cable from the current monitor on the module into an oscilloscope. On our manual control board, we will switch both dip switches to the right for external current control and external potentiometer control. Then we will adjust R40 to make sure we're at mid scale. So we're going to try to get about 100 amps out of this 200 amp module. It's a 20 turn pot, so we'll turn the pot one direction fully and then turn it clockwise. If you want counterclockwise, we'll turn it clockwise 10 turns to try to get it to mid scale. We'll install the 12 volt power source via the banana jacks. Next, we're going to enable the 5 volt power source or the 12 volt power source, and I wanted to point out that the red LED, the status LED, turns on, and it's going to be on for approximately 10 seconds. And in that time, we need to enable the DC input power supply. Here's our DC input power supply. So we're trying to go to mid-scale on this, and it's about 100, 110 amps. So we're going to set the voltage, knowing that our load is 0.196 ohms, knowing that we have 110 amps, roughly, and we're going to give it 12 volts overhead. So we're going to set this power supply to 34 volts. If you turn on the DC power supply and 12 volt power supply in the right sequence, you'll find out after 10 seconds the status LED will go off, and that now the system is ready to be enabled. So before we enable the trigger source, we're going to make sure all our settings are within the safe operating area of our graphs that are in the data sheet. We've already done that here. So we'll enable the output. And here is the current monitor that we're seeing on the oscilloscope. I want to point out that our scope is set to 50 ohm impedance and a 1-to-1 probe. So this calculates it into roughly 110 amps. Here's a view of the entire system except for the DC input source, which is out of frame. So looking at the picture on the far left is our 12-volt input source. And the next instrument over to the right is a Tektronix function generator and our module, and then the oscilloscope where we're monitoring the input current. And on the back right, you can see that green box, and that is actually our load. Solutions to common problems. So the red status LED, it only comes on for 3 conditions. One condition is on power up. It's on for 10 seconds. We talked about how you must enable the DC input source within that 10 seconds for it not to fault out. The second is open load fault. And if either one of these fault conditions is detected, you will have to go through a complete shutdown and power up sequence to reset the error. So you must always make sure your DC input is over your forward voltage of your load by 12 volts or so. The next fault is thermal fault. You really need to check your liquid flow. If you have good liquid flow, then you need to check your safe operating area graphs to make sure you're using the module within a safe area. Other problems you could see is ringing or maybe distortion on the output. So the biggest problem here would be not having your DC input voltage set properly. So review the data sheet, make sure that your device at that current range, you're satisfying enough voltage for that. The second thing is not connecting your laser properly to the load board. It's very important to use that load board or one that you make yourself so that we reduce our inductance as much as possible.
The PCM 7140 is a powerful, flexible, affordable, liquid-cooled laser diode driver module that can jumpstart your design process and meet your OEM integration needs in manufacturing. Contact Directed Energy and find out how we can help you from lab to launch.